present. Welcome to. And as usual, we will have a presentation by Parisee for about 45 minutes. Then you can ask whatever. Of course, you can ask anytime. Now that you are here, you can stop here and ask questions. Officially, we will have time for you to ask a question before we allow audience to ask the question. Okay, Parisee.
I'll be. It's a 287-page thesis, so it would have been a considerable thing to read. But in these 45 minutes, I'll try to give you a brief idea about the work undertaken in the thesis, rather than going into too many details. And then I'll go into the details based on the questions that are asked. The focus of the thesis has been on the beams, radiation, X-ray beams, and emanating from a special class of pulsars called binary accreting X-ray pulsars. There are 4 publications included in the thesis. 2 are published and 2 are on the archive as citable sources. To give you an idea about the pulsars to begin with, the image on the left is by far the most accurate depiction of these objects that I've come across. Matter is being accreted from an optical companion, and that powers these X-ray beams. The way these are observed in the sky is pulsed X-ray flux. So the X-ray flux increases and goes down periodically. And this is not intrinsic to the source. It's only because the rotation and magnetic axis are misaligned. So the pulses are, when the beams sweep across the observer's line of sight, the pulsations are not intrinsic to the source. A closer picture is matter being accreted from the binary companion, gets obstructed at the magnetic field of the pulsar. It then gets threaded onto the magnetic field and then funneled onto the magnetic poles of the pulsar. The rotational poles might be different from the magnetic poles, which is why it appears as a pulsating source. One of the main unresolved issues regarding this is the pencil and fan beam degeneracy. So this beam, either the photons can emanate along the beam, or the photons can emanate from the perpendicular to the beam, that is from the sides of the accretion region which has formed. So it seems like a basic problem, but it has been unresolved till date, which basically means that when the pulses, when the X-rays are highest, as seen by the observer, you don't really know whether the pulsar is pointing right at you or it's pointing away from you, and you're getting the fan emission, which is actually from the sides. There have been several X-ray telescopes launched over the past 50 years. These have tried to perform spectral and timing analysis of these sources. There will be new telescopes launched which will focus on the polarization characteristics. This work tries to make use of some of the AstroSat observations. ExpoSat has also been launched recently. The first part will focus on numerical simulations of these beams. I've written a code that tries to model these, produce these profiles for a wide range of input variables. The first thing you try is, in the literature, the profiles are available for a limited range of configurations of the pulsar. When I say configurations, this is what I mean in the diagram. The orientation of the rotation axis and the magnetic axis are any of these combinations can be encountered in the galactic plane. These can be randomly oriented based on how we observe this pulsar. So it's good to know such profiles for any arbitrary inclination of these axes. The beams, of course, are modeled. So I will be using those model beams and then seeing how an observer on Earth can observe these beams as pulses based on any possible random orientation of the pulsar. The picture on the left is like a maximal or more contemporary idea about what this work is. The picture on the right is a minimal physics textbook kind of a diagram. The work itself lies somewhere in between, but derives from both these ends. The picture on the graph on the left are the model beam emission, which are known in literature by performing radiative transfer in the accretion region of the pulsar. The beaming function is basically how the photons are escaping with respect to the magnetic axis of the pulsar. So 0 corresponds to along the axis and 90 degrees corresponds to perpendicular to the axis. This is for slabs, which means it's for pencil beam, so it's high for along the magnetic field. For columns, which correspond to fan beams, they will be high perpendicular to the magnetic field. I have tried to take both columns and slabs into consideration in the thesis, and I've also tried to do this for two optical depths, so shallow slabs, shallow columns, and deep slabs and deep columns. So 4 of these can be dealt with by the simulator. On the right, I've just tried to emphasize that once the radiative transfer has been performed, the beaming function on the left can, if suitably replotted, can give you an idea about the overall radiation escaping from the beam. And if suitably replotted, it can also give you an idea about how the spectra look like at different angles escaping from the, with respect to the magnetic field. So the first chapter has to do with constructing such a pulse profile simulator in this thesis. This will function as a base code on top of which additional capabilities can be added to enhance its features. But the first one is a direct and exact implementation of the pulsar rotation. So the first equation tries to relate I1 and I2, which are the rotation and magnetic angle inclinations, along with a phase phi here, which is the phase of the pulsar rotation, and tries to calculate theta, which is the direction which an observer on Earth will end up sampling. Using this direct implementation, you get, for an arbitrary value of I1 and I2, you can get an idea about the pulse profile which will be observed. Now, in the paper I've tried to keep it consistent with the previous reports in the literature, which are about 160 pulse profiles for sample inclination angles and so on. But the code itself can handle any arbitrary value. Second, you try to add another feature. I have not shown the results of those pulse profiles right now. I'll show them collectively later on and also give you a comparative view of how the pulse profiles change as you add more and more capabilities to the code. So this part is trying to add general relativistic modifications to the pulse profile. I have shown in a subsequent chapter how significant this effect is in modifying the observed pulse profile as the photons traverse the strong gravitational field around the neutron star. The trajectories will be slightly bent. So the emitted beams are different and they get slightly bent. And therefore, the observer on Earth can see highly modified profiles. This is the equation which we tried using. It's Belaborodov's approximation that relates the outgoing angle, so the launching angle of the photon alpha, to the angle psi, which is the asymptote of the photons towards the observer's line of sight, through the parameter u, which measures the strength of the gravitational field. Implementing this, you have some idea about how the profiles will change again through gravity. You're expecting the overall broadening of the beam, more smoothing of the pulse profile. Another second effect is gravitational redshift. Here, the photons lose energy as they escape from the gravitational field of the neutron star. The effect takes into account how the region from where these photons generated. So if they're coming in deeper from the gravitational field towards infinity, then they end up losing more energy. This effect is, there's a standard formula available for it and is more pronounced for harder energy X-rays. There are other effects also, relativistic effects, which can come into picture, which I should mention for theoretical completeness. I've tried to defend in the thesis why these may not be as relevant for this class of pulsars and that they might be more relevant for accreting millisecond X-ray pulsars, which are far more fast rotating. one of the things which stood out in this particular exercise, which I will present right away, is the hypothetical possibility of observing an X-ray Einstein ring in limiting masses, because the X-rays bend so much that beyond a certain extent, any photon which is going towards the back or the dark face of the neutron star is still bent towards the observer. So you essentially see it as a non-pulsed. So you will still see it as a stationary source, no rotation in there. I've tried to also test it for an isotropic emitter, taking a test beam that doesn't channel photons along a single direction, but emits equally everywhere for the sake of comparison. Even in an isotropic emitter, you will see that if you go from this plot to this plot, then there is a higher emission when the second hotspot kind of goes behind in the dark face of the neutron star, because you still have the background photons being bent towards the observer. I have tried to take that into account. So yeah, I've tried to model that as well. This is the third effect which can come into play if you're looking for realistic descriptions of the pulse profile. This here tries to resolve the point emission approximation, which is you just consider one beaming function as if it's just emanating from a point. But that is not the case. There are more sophisticated geometries of emission which are available. And this takes a step towards that. Instead of using a point, I have accounted for a circular slab, and I used polar coordinate geometry to break that slab into a radial and azimuthal grid. Now the difference here is that each one of these single points is going to beam photons along the magnetic field and then perpendicular depending on the beaming function. So the observer ends up observing a differential emission angle. So along the line of sight, you don't just have emission coming from the center of the hotspot, but also slightly different emission angles that need to be integrated over the emission region. Here it's taken as a circular slab. To give you an idea, this would have to be a double integral over a closed surface, and there are two hotspots. So you need to account for both. And you also need to account for if suppose the second hotspot is only partially visible, then only you will not again get radiation from the entire hotspot. You will only get like partial radiation, and composite with GR, only that part which is again, bent towards you. So you need to choose your integration surface carefully. And for the implementing the differential angle, we thought of coming up with this analogy between the pulsar rotation formula and the differential emission angle coming from the circular slab. If there's a clever trick here, but if you notice the similarity, a simple replacement of the variables can help you come up with a cleaner algorithm for implementing this computationally. The pulse profile simulations now up till this point are shown here. All the 5 columns correspond to the same orientation here, which are shown for 45-45 for comparison. But in literature, I have reported this for 5 different angles to keep it consistent with the previous literature. On the right, each of these rows correspond to a different X-ray photon energy. And if you track boxes with a similar color, you will see how the profiles for the same pulsar are now changing just by adding different effects. The most prominent one which I would like to focus on though here is the yellow box. So here, if you go add GR, then you can see that there is basic appearance of the pulse itself changes, and the most prominent one being that the hump, which is here, has now gone on to be here. So the profile broadens, and there's also a slight increase in the flux. When you account for the second hotspot, there's again an increase in this emission, which is observed at 0.5.
What is the difference between this both and the tip profile?
And okay, so this and the tip?
Yes.
Yeah, so and when you include the effect of the surface integration, which is that it's coming from an extended emission angle, then you will see that the emission is again going higher. So you basically end up receiving more and more emission as you go on adding GR and extended geometric effects. That is what is seen here. Then there are other boxes, of course, which show you more of these features. It's also seen here, for instance. You're getting more, it's less sharp now because it's not like coming from a point. It's a simplistic approximation. But as you go on adding, accounting for more realistic scenarios, the profiles are more broadened out, more smoothened, and overall give you a higher flux.
So mostly it is based on approximation.
The first one is an approximation. I tried to include, I tried to remove that approximation and go towards more realistic scenarios. But implementing those and accounting for those very fine effects is computationally challenging. So it's an effort. Like for cylinders, for instance, you would have to account for accounting for gravity along the height of the column. Again, there will be a gradient of the, so they will be differentially shifted, for instance. So the computational implementation is what gets slightly difficult while going towards realistic scenarios. But I've still tried to compute this in a way where it remains scalable again in order to go towards more realistic scenarios. On the left is a plot that gives you an idea again of what happens when you replace the point with a circular slab. The emission is initially, the curves below correspond to 10 to the power 28 flux units. But then when you integrate both of these over an emission slab of about 1 kilometer square model area, both of these curves now become the topmost curves, which become, oh sorry, the top ones are for GR, the bottom ones are without GR, and the red curves are for slab. So the flux units for slab itself is basically different, and it grows by about 10 bar 10 orders of magnitude, which is more known for standard ballpark for X-ray pulsar flux. I'm bringing the future scope slide beforehand. I will not be presenting it later, just to emphasize that the code, because I've tried to implement the circular slab geometry, it can be extended to, say, for accounting for crescents as well by like suitably adding or subtracting circular hotspots, for instance, accounting for multi-temperature components. On the right, I'll lead you into the next part. This is a slide from my topic of course presentation, actually, where I presented on the decihertz space-based gravitational wave detection. Over there, it was a paper which discussed its science potentials, and the last slide, which discussed the most difficult case, was on the detection of tertiary mass sources. If a GW source is in the vicinity of supermassive tertiary mass, then the gravitational waves are modulated by a Doppler modulation, which is given in this formula. We had tried doing a very similar thing in the case of X-ray binary sources, and in the entire pipeline of how these sources would need to be analyzed, it would be this part of the Doppler modulation, which we would be looking into now. So the second part will now deal with more astronomy. This particular part where I've analyzed some astrosat observations is the part where I've used some external codes or external software. Rest everything has been coded ground up using Python. Now the thing with the observed pulse profile is up till this point, I was still talking about pulsars which would be stationary. It's just the beam and the effects which will modify the profile as we see it. But if you think of it as a lighthouse, then it's not just a lighthouse which is rotating. It's also, because I deal with binary pulsars, it's also going about an optical companion. So it itself is an orbit. So this orbit needs to be subtracted out. And because these are X-ray observations, these have to be detected in space. So you have a satellite as well, which is going around. So these need to be subtracted in. So this is analysis of the LAX-PC data on board AstroSat. On the left are the preliminary pulsations that can be easily seen as detected by the detector. But towards the right, I've tried to emphasize the binary nature of the pulsar. If hourly bend time curve will show a growth and then a decay, which means that the pulsar is coming towards us and then going back. This is also seen if the pulse profile is bent on slightly shorter time scales. If you see here in the GIF, then the peak kind of goes to the left and then back again because the pulsar is again coming towards us and back again. This needs to be subtracted out. However, even after modeling this with this Doppler modulation formula, there might be, like, I have come across other more phenomenological formulae in literature which can be used for implementing this computationally, but this is something that we tried out here. And after subtracting for this Doppler modulation again, because the Doppler formula applies for circular motion, we still have this residual trend remaining in the data arising because of the eccentricity of the orbit. The fact that its periodicity is again about half of the binary orbit period further lends weight to this. Once this has also been subtracted, you can have measurements of the intrinsic pulse profile, which basically mean you have subtracted the overall effect of the binary companion, and now you can assume that the pulsar is stationary. So with this, now you can do more with the data, but the focus here was about how to go about subtracting that. And finally, you would have energy resolved pulse profiles with the energies increasing towards the lower end. I have tried to keep to the higher energy end while proceeding towards the next chapter, because these are typically higher energies being more penetrating, they interact less and present smoother profiles. It's also more symmetric in nature, which is arising out of a dipole approximation, which has gone into my simulations to the right. The secondary pulse, which is observed, secondary hump, which is observed here, which seems to decay towards the higher energy end, is a telltale sign of a distorted magnetic field, which remains what is commonly found. Now, to go forth, I will be comparing my observed results with the numerical simulations, and I then choose a suitable energy bin, which is available on both ends. So proceeding with 15.2 keV, if I input the known Centaurus X3 inclination into my simulator, then I get several simulations, and then I try to compare which one best fits the observations and try to make some systemic inference. The fifth chapter focuses on exploiting this comparison now to extract some astrophysical inference about Centaurus X3. In this particular chapter, I've tried to add another module, the surface coverage module, that varies the size of the hotspot from 0% surface coverage, which is 0 kilometers, all the way up to the hemispherical circumference, which is 100% surface coverage, and simulate the pulse profiles accordingly. The red curves corresponds to the standard 1 kilometer square model, and then you go on increasing. For this particular thing, you have to replace the initial polar coordinate grid, which is sufficient for a small circle, and you have to modify that coordinate system with a spherical correction, which can account for polar caps, which are slightly circular in nature when you are going to go to higher surface coverage. So this generates a whole family of plots. I've tried to divide them into two based on their appearance. The first one, again, it shows how the profiles are changing with an increasing surface coverage as it goes towards lighter gray. The second one gives you an idea about how, for comparison, if I change the input to the code and provide an isotropic emitter, then it should provide a reasonable change in the output as well, because the code itself should not be designed to provide a certain kind of input itself. So with that in mind, I primarily focus on the left-hand side. So here, now both these curves again can be composite with gravitational light bending and without. So I've tried to generate that entire family of curves and then measure how the pulse fraction is changing. This is something that we thought of, that pulse fraction could be used as a robust estimator to try to proceed with comparing better with observations for systemic inference. On the dotted curve is off the surface. As you go on increasing the surface coverage, the pulse change in the pulse fraction, if you have gravitational light bending included. And this non-dotted curve is without that effect. Now the horizontal line corresponds to the observed pulse fraction for Centaurus X3, and both of them do intersect both of these curves. And the points of intersection, if they are suitably geometrically converted into the computed hotspot radius, then it is seen that the incorporation of light bending gives you a hotspot estimate, radius estimate, which drops by an order of magnitude over here. This goes on to emphasize the importance of the distortion which might be produced due to gravitational light bending. I've also tried to include a discussion on the pencil and fan beam degeneracy here, but I'll probably look into it later, towards a later slide. The third part deals with trying to do some physics with this system. The first part tries to use neutron stars as fundamental laboratories of fundamental physics. Any X-ray telescope which is being launched, typically, if it's accompanied by any white paper, then I've come across at least one paragraph in each of these papers on how neutron stars are excellent laboratories for testing fundamental laws of physics. This particular chapter will make use of vacuum birefringence and take into account this vacuum effects and how it impacts, leads to polarized expectations of polarized radiation from this particular source. This is a purely vacuum effect arising because of the strong magnetic field. I'm moving out of GR for this one. A new window is opening in the high energy band where almost every telescope going up will have a polarimeter on board. This is what is shown to people, but this is what the real work looks like. Accounting for these vacuum effects would need you to take into consideration resonant differential cross sections to completely account for the photon plasma interactions and the absorptions and scattering interactions, and take the plasma properties into consideration through through its properties of how it would interact with the outgoing X-ray radiation. So I've tried to unveil some of these algorithms. Like the final formula you will find here and there in the literature, but if you were to computationally implement it, it has to be heavily broken down into pieces. There is a vacuum factor which comes into account, and photon mode switching from O to X and X to O is again possible. So all of those need to be tracked. Furthermore, you would have to make, I mean, these are the cleaner equations, but these would have to be made dimensionally consistent again. So, but eventually, if such an exercise has been done, which has been included only on a proof of concept basis in the thesis, then tracking such photons through a radiative transfer grid would be able to produce expectations of polarized radiation for a large number of input variables. Polarization itself hopes to add 2 new dimensions to the existing space of spectrotiming analysis. If such a device is made, then it could immediately help you decipher the systemic configurations provided a certain degree and angle of polarization has been detected. I have only cited the initial Turing papers though, because the advanced versions needed to be reprogrammable. This would not be required in this case. So theoretically, again speaking, I have provided the algorithms in the thesis, but taking these photon plasma interactions, you would be able to get some idea about both the vacuum polarizations and the scattering polarization arising from the scattering in the accretion region. This polarization vector again would need to be tracked as the outgoing photons traverse through the strong gravitational field around the neutron star. And these algorithms have been appended to the thesis. Finally, on the physical characterization of the system, the earlier chapter discussed neutron stars as fundamental, laboratories of fundamental physics. This one is directly very related to laboratory physics itself. If you forget the pulsar, then you can think of this system as an accreted plasma suspended in a strong external magnetic field and irradiated with a polychromatic X-ray source. Now, there are 3 free variables in this, which is the velocity of the plasma ions, the energy range of the X-ray radiation, and the strength of the external magnetic field. So like physics students regularly do in a lab, you can vary all these 3 parameters and see what are the effects. To go into slight more detail, I will be computing Gaunt factors for these cases. Gaunt factors characterize the electromagnetic and radiative processes in these systems and eventually go into the calculation of opacities and optical depths. Here in the external magnetic field, Gaunt factors would have to be divided into 2 components, parallel and perpendicular. I developed a calculator for this. The base version will basically spit out the Gaunt factors for a particular value of X-ray photon as if it was monochromatic for one interaction, basically, and the external magnetic field. And then the more advanced versions allow for greater variations in each of these parameters. This is a map. You get the left-hand side is the perpendicular and the right-hand side is the parallel Gaunt factor. These have been presented for model values of X-ray photon energy, which are available in accreting X-ray pulsars, and model values of the cyclotron energy, which is the strength of the external magnetic field. Both of them are allowed to vary in a discrete sampling way over the entire available range, which is possible in observations. I have also allowed the plasma temperature to vary now. So all the three parameters have been set free. In this, if you take away the discrete sampling of the photon energy and allow it to vary continuously now, the factors now get replaced by Gaunt curves. And to get more out of the computing capacity of the desktops that were provided to us, I also tried to vary the cyclotron energy or the external magnetic field strength in a very fine sampling way, so that now gives me Gaunt functions. So these characterize the physics of the systems. These are some of the main references which have been used in the theses over the past 50 decades, but the primary one remains the Mazaras and Nagel papers. This was a milestone paper about 40 years back, the code for which has been lost. And this was recently hailed as a precious attempt to try to revive work like that. To give you a quick idea again, to put all of this into perspective, the code tries to account for a wide range of input parameters at the source and also predict a wide range of observables, trying to take realistic scenarios to the extent that we could possible, but this is scalable again. It's not exact yet, but it's a step in that direction, and I've tried to show what was possible for me to do within this time span. Second thing I wanted to emphasize, going back to the pencil and fan beam problem, one of the promises of polarization studies is that it will give a decisive blow to this pencil and fan beam degeneracy problem. Polarization signatures are expected to be completely distinct for either of these two cases, which is why they are looked at as the final thing which can discriminate between these two cases. But through my studies, I did notice some features here and there, which did allow me to comment on this degeneracy, irrespective of the polarization features, purely from a theoretical perspective. I have tried to outline them in the thesis. One of them was back when I showed you the energy and luminosity dependence while comparing with observations. So there are some features that change and show distinct signatures for either of them without me needing to know the polarization signature for these observations. I have also in the thesis tried to, but I was less confident with that one because it's not my area of expertise. But I did try to also suggest a way in which these could be related to the neutron star radii through the equations of state and see whether you could find some probes through that. But before I could get to trying something of that sort out, I was recently asked to review exactly that paper. Now it's not available on archive, so I don't have a citable source for it. But I guess I'll be contributing it to now more from the point of view of a reviewer than an author. Just to back up this idea, I have some recent, some work is being done in that space as well. Now, I mentioned that this I've tried to, because it's a thesis again, so I tried to make this as comprehensive as I could and touch upon all the relevant aspects. I've tried to incorporate all the physical effects which might come into play and tried to incorporate as many physical conditions as possible. Classes of observation wise, I had to limit myself to light curves because they already showed so much more promise than we could get. Like it could be, those studies could be extended further for like geometric and physical characterization, and you could go deeper into it. But such work could be extended, and those algorithms are provided in the thesis, how this could be extended to incorporate other classes of observations as well, especially taking a step towards a unified theory overall of X-ray formation and going over a large range of accretion luminosities. Right now, the work which has been done is a bit of a bootstrapping approach where people try to see where they can comment, and it's limited to that. But ideally, it would be good to take a lot of luminosities into account. So from my pre-PhD seminar to now, a lot of the publishable or citable sources which would be expected from the theses have been prepared. The only one which is left right now is making this code open source. So, but that will be done eventually. Yeah, I'm done.
Yeah, I just want to know that if you see your title of the thesis, it's written there this human division. So what's the present status? Is anybody doing some work on human division? Right now?
Being some, these are routinely dealt with.
I will do the review.
In the literature review section, I have tried to mention some of the work which has been done in this particular regard. Of course, you can, or even this new paper which I got, they deal with beams only. So the beamed part basically talks about the anisotropy or the directionality, but it has been routinely done because that is a very prominent feature of the pulsars that sets them apart from other classes of observations. So a lot of work has been done and is continuing to be done because that remains the primary feature that people use.
And the data that you have used, the data you have
2016 December.
2016.
Just
2016.
Just, yeah. 2016.
Was that only that?
That was the one which was available with my faculty member, but there have been more studies. Yeah, so if you see here, it has been, it's a routinely observed source because we chose that as a model pulsar because it has a circular orbit. So for it to remain a cornerstone exercise, that can be scaled up. But for instance, somebody else also observed it around the same time and provided independent confirmation of the conclusions or the conclusions about the system which we drew. Along with that, there was a group at IIT Bombay that tried to use the same observations, put it together with more observations later on, and write a dedicated timing paper on this work. And this has also been cited in this paper from RRI, where they mentioned that in general, it is if for timing purposes, if that is the focus, then any number of observations as long as possible is always but yeah, this one again uses the 2016 data. That's correct. For our case, it was more about the theoretical modeling of the binary one. It was not a timing heavy thing.
When you talk about this rate which affects the light coming from the different stars, so you're talking about these bright pulse profiles.
Brighter pulse profiles, as in you end up getting more flux because the beam gets curved. So for a certain angle, you actually end up getting beams or radiation which has been emitted closer to the magnetic axis, which you otherwise would not have received. Is that clear? Like I can draw on the blackboard and show you. But for a particular angle, if you are going to get some radiation, because of light bending away from the magnetic field, you actually end up getting stronger emission because now you're able to see a region which you otherwise would not have seen, which has actually gone out of view. But because of light bending, you continue sampling the same region because the trajectories are actually bent. It's not straight. And again, adding to that, the second thing that comes into play is you also end up getting photons, which are from the dark face of the neutron star, which are bent towards you because of gravity. So two things. That's why it increases. Without gravitational light bending, you will just see whatever has been thrown towards the line of observer's line.
And regarding how many publications you have now?
There are 4.
At the time of the submission, you had 1 and 1 was under preparation.
Yeah. So, yeah.
So, have the other 2 come in this?
The other 2 have been uploaded on archive, and actually the work in there I then divided into 3 parts, and the third one is published.
So now it is open to anyone who to ask questions.
The plasma one is the one which I had sent.
Yeah. Very good, slide 28.
This one?
Yes. But we don't have mic, right? So maybe if somebody is online, they may not listen to our question. Maybe you repeat the question before.
No, it's a very short question. So with 100% surface coverage, you still seem to get pulse fraction.
Yeah, because the beam itself, like I said in this case. So on the right here, I've used an isotropic function. So it's like a fire, basically, you see it anyhow. But on the left, we still need to have the external magnetic field on the pulsar because the pulse, it's not like a fire. The emission is beamed in a certain direction. So that's why even if it is 100% coverage, there's still a magnetic field which prefers to send the photons in some preferred direction. Pencil or fan is a question mark, but there's still a direction of preference available in the system. That's why. So even if it's 100%, it means you're going to sample those many angles now, but they're not all equally pointed at. Yeah, emitted at you.
Any other questions?
Can you explain why the transport radius is considered to such great accuracy?
Oh no, that is just because of the way the intercepts are there. So I wouldn't actually take these estimates to be like the final word or something. The main, the preliminary point of this exercise was to see the drop in the estimate, basically, of the estimate you have of the hotspot size. So here you will come at a figure of about 12.27. The error bars are not significant, of course, over here, but that is just a byproduct of the way of this exercise, basically. But here again, once you put in gravitational light bending, you get a estimate which is fairly in the ballpark of the expected. So that's it. That's the only point of this exercise. I wouldn't really oppose this as, we have found out the radius of the hotspot.
Is there anybody else? Sure.
Yeah, so one more. Yeah. So on the hotspot, and just a hypothetical question. So are there attempts to model the hotspot itself as some sort of a structured hotspot?
Yeah, so there are more intricate geometries available. He has worked on accretion mounts in his thesis. Although they don't have that much observational evidence, but those are discussed. Then I have dealt with slabs and discussed columns in depth, but like I showed in this slide, there is work which is routinely done in trying to see what they look like in reality. So this was a paper in the RJ Letters special issue reporting nicer results where they actually found that there might be multiple hotspots present. They could be oval in shape, there could be crescent shapes. There are filled rings which are possible, so only the circumference is emitting and not, which is why I call this a scalable exercise, because once you have this initial exercise ready with you, once you think of it, it's easy to then scale it up to others. For example, if it's a filled ring, then you just need to subtract any emission which might be coming from the interior, basically. And then depending on the width of the ring that you would like to have, you might want to subtract suitable. But the initial thing needs to be there first, the implementation. And hopefully with more newer missions going up, you'll again see more and more intricate structures. Like I think of them as like sunspots you have on the sun. It's brutal to actually just say it's going to be a perfectly circular slab exactly placed on the magnetic pole. These are more intricate in there. But clearly, because it's a very small, it's a compact object, so resolving these structures, and you can't image again. So there's no imaging. So only indirect inference is available. So people go into great statistical depth to just try to see if there's a different possibility available. Here they reported crescents and ovals and multiple, like 2, 3 in combination. So
because with the structured hotspots, there may, because of the linkages to the magnetic fields, there may be possibility of interacting hotspots. So one could
He's going in depth. Yes.
Also, that it will introduce degeneracy interpretation.
Yeah, that was my second thing. That then what kind of degeneracy you expect in the pulse profile?
As far as I've come across all of these modeling attempts, because those are also, I mean, there's a great deal of literature available over there, but they've not been able to all go down to this level of accuracy. And despite the large body of work, these kind of structures were only reported extremely recently. So to the extent I've seen, they all treat the dipole, one of these as one solid region, and they have a size estimate that too. No precise measurements have been made so far. That's why I again said these constraints themselves, yeah, here cannot be very precise, because typically it's just taken as a 1 kilometer square. I've tried to do such a thing over here through the information available to me. But it was interesting for me to see that one could go in that direction to begin with. But otherwise, people just take it as a 1 kilometer square emitting region. Now there are some ideas that because of the penicillin slab, it could be a slab or it could be a accretion column. So again, there are more depths, and then other things also tend to probe the physics of these systems again. So that is another branch in which things go. But yeah, there's multiple things and all are coming in right now, I think. Typically, they just think of it as one, solid emission body.
Is there any other questions? I have one question. So when you showed the pulse profile as a function of energy, you mentioned that going to the higher energy is good because the profile becomes symmetric while you are doing it. So, but actually, most structures are interesting, right? That is where you.
Yeah. So this.
So why at low energy you have more structures?
Probably, like I heard this in one of the lectures that I was attending, that maybe because this is lower energy.
Those are observed ones.
Yeah, this is observed. On this part, it's observed, and these are my simulations from geometric considerations. And with increasing energy is upwards. Here it's downwards. So there are more features on this side, and like you said, it's more interesting because, for instance, you see a secondary hump over there, which points to a distorted magnetic dipole configuration. It's a direct signature. But for the same pulsar, if you go towards higher energy, it's a more smoother. It doesn't really give you that information. But for comparison with this thing, I wanted, because a symmetric dipole approximation.
So whether it is the radiative transport effect or emission effect. So the physics which will give you 3 kV emission may be different from the one which gives you 30 kV emission. Or if you take 30 kV photon, which can travel through the medium very easily, whereas absorption cross section will be higher for low energy. Do they discuss? So this is another thing which brings in, right?
Yeah. So this is very rich in terms of its physics, and there are a lot of things that go into it. From the best that I know, because this particular feature is arising from the distorted dipole, this will come from the radiative transfer, like the way it is propagating in the medium. It is not about the way it is generated in the medium. I wouldn't be the expert to comment on the generation of these photons. The only thing I know about the photon generation is it's Bremsstrahlung radiation, so breaking.
No. In your case, you would say whether you have area dependent on frequency. If you you project the problem into your case, right? So this is what the structures comes back to the structures within. Anyway, if there are no further questions, I hope that both the examiners are happy with the presentation and the way she answered to the questions. With their permission, let's congratulate Parisee for successfully defending the congratulations.
I'm sure that
I saw that.
Okay.
I think you might.
equipment
What about you?
Nice to know.
I don't know what. One day over the conference from there.
See, where from here? Where from Maharashtra?
Yeah.
Have you logged out of the Zoom? Can you show me the Zoom participant? Dipankar, hi. Can you hear me?
Yes, I can hear you.
We
And
finished,
congratulations to Parisee.
Thank you.
we finished the proceedings. Thank you for.
Yes.
We'll also log off now.
Okay. Yeah. Bye bye.
Bye. Okay, policy. Rest.
Almost explaining us to it.